Hello and welcome back. We are working on section 2.5. We are in the second half. 2.5 is about lines and planes. We talked about lines already, so now we're going to concentrate on talking about planes. So the first thing we need to do is to be able to find equations of planes. And let's take a look at the objectives. So objective is to take a look at finding the equation of planes and expressing it in vector and scalar form. I have to admit that most of the time we want things in scalar form because then we can express the equation of the plane in terms of x, y, and z. Vector form is a good way to actually create the equation, but we're going to focus more on the scalar form. So what do we need for an equation of a plane? So a lot of people might say 3 points, and that does make sense. That's equivalent to saying in 2 dimensions, what do you need for an equation of a line? You say 2 points. Great, but then first thing you have to do is find a slope because you really need a point and a slope. We saw that in for finding lines in 3D, we need a point and a direction because a slope no longer works in 2 dimensions, or it no longer works in 3 dimensions, so we need something else that would define some sort of inclination in 3D. So the best way to do that is with a direction. Now for a plane, if we have points, let's say we have points on a plane, we have 3 points on a plane, we can certainly define a plane just like we can define a line in 2D with 2 points. But what do we need? So if we connect these lines here, or these points here, we just see points on the plane itself, but it's still not distinctive. In fact, from one point on the plane, we can see a bunch of different directions and too many different directions that we can define, and so none of them would clearly give us the equation of a plane. So the best way to get a quote direction of a plane is to use or is to find a vector that's perpendicular to the plane. So that is called a normal. So I know that perpendicular, normal, orthogonal, there's a lot of ways to describe the idea of perpendicular. Why can't they just use that word perpendicular? The answer is I don't really know. Maybe it's too long to say, and so they say orthogonal, and then that's too long too, so they say normal. I don't know. In any case, if we find a vector that's perpendicular to the plane, that vector can be the one vector that can uniquely define the plane. Now, I know with vectors, you can move it around. And also, by the way, you can change the length of that vector and maybe even change the orientation, make it go the opposite way by negative, and then you would still have something perpendicular. So there's a lot of ways to express the normal vector. So this will help us actually define the plane uniquely. All right. Now, how are we going to do that? So we're going to suppose that we actually have a point on the plane, and we'll call that point, maybe we'll highlight this point and call that point x naught, y naught, z naught. So that's a point on the plane. And then we have the normal. So I know we have 3 points, but you can really just do it in one, and that 1 point and a normal vector will define the plane. Now, what we're going to do is we're going to pick any other random point on the plane. So some random point x, y, z, and we'll just randomly call it x, y, z because it could be anywhere as long as it's on the plane. And these are the x, y, z's that we're describing as points on the plane. And what we'll do is we'll make a vector connecting x naught, y naught, z naught, and x, y, z, the arbitrary random point on the plane. And then now we have a vector on the plane. So remember, that vector on the plane was not distinctive enough for us because you can have a million infinite number of vectors on the plane, but the normal vector is what's going to help us find the equation. So regardless of where your x naught, y naught, z naught is, as long as it's on the plane, then that vector connecting x naught, y naught, z naught, and x, y, z has to be perpendicular to the normal vector. So there is this equation over here that says n dotted with r minus r naught, which is that vector that's on the plane. So let's actually say vector on the plane. And that has to have a dot product of 0 because it is perpendicular. Now, you can also distribute the n, the normal vector, because there's a distributive property for the dot product. And then you can bring the n dotted with r naught on the other side, so you might have an equation that looks like this. So both of these are in vector form. Again, vector form is not that helpful for us, but it does help us get to the scalar form, which is going to be how we will be expressing most of our equations of planes. So if we do this by component, n, if you recall, was just the vector ABC, and then r is that arbitrary vector with x naught, y naught, z naught, and then r naught is the specific point on the plane that we found, x naught, y naught, z naught. Okay, so if we put those components in, we know that ABC is n dotted with x, y, z. That product is going to be simple, and this one is also not bad. But the interesting about this is that this is going to be a constant. So let's call that constant d. So we'll replace this right-hand side with just the scalar number d, and then the left-hand side would be ax plus by plus cz. So if you have ax plus by plus cz on one side and d on the other side, you have now a scalar equation. So a, b, c are scalars, d is a scalar, and then x, y, z are scalars that are your variables that represent the points in space. Okay, so this is going to be our equation. I have to warn you that I think some textbooks, maybe even our textbook, uses a different form, a slightly different form for the line, and I'm going to put it here and then quickly cross it out. Sometimes they use ax plus by plus cz minus d equals 0, or sometimes they use plus d. If it was a minus d, then it's pretty much equivalent to what we have. But if they put a plus d, I think that sign of the d will make a difference in the plane. So, but I think that's how some books have it, and I don't quite remember how our textbook has it, but I like to use this form myself because it puts d on the other side and we just focus on the value of d. And remember that the value of d is going to be the dot product of the normal with that specific point on the plane. All right, let's do a problem. The first one's going to be rather quick because we are given what we need for an equation of the plane, and then we can simply use the formula. So the equation of the plane passing through the point, -3 to -1. So that's going to be our x naught, y naught, z naught. And the normal vector is going to be 1, -1, 1. That's going to be our a, b, and c. So let's just label this x naught, y naught, z naught for our point, and then a, b, c for our vector. Now, the left-hand side is going to be just a, b, c is coefficients of x, y, z, and then the right-hand side is going to be d, which is a dot product. So let's compute d first, and then we're going to treat this point, -3 to 1, -1, as if it was a vector, and we're going to dot it with 1, -1, 1. Now, vectors are points, points are vectors, points are vectors in standard position and stuff like that. So I'm feeling okay about doing this. And then we have -3 times, and then times 1, and then 2 times -1, so that's a -2. -1 times 1, that's -1. So I think get -6 for this. And so your equation of the line is going to be a, so that's 1 times x, -1 times y, so b is -1, and c is +1 times z, and then equals -6. All right, let's take a quick look at the Desmos version of this. We have a point. This is our point, and we have our vector, and our vector right now is in standard position. So just for the sake of making this look like the equation that we want, or the normal vector that we want, let's put that normal vector on the point. It doesn't necessarily have to be coming from the point, but if it's coming from the point, at least we can see when we draw the plane. And so let's create an implicit plot for the plane, and I think that was x minus y plus z equals -6. And we can see that plane here actually contains a point, and if we look at it at just the right angle, it looks like that normal vector is indeed perpendicular to that plane. Okay, so that's good. And let's do one more problem. This time we are looking for an equation of a plane that has 3 points. So 3 points actually can uniquely define a plane, but we eventually need a point in a normal. So let's imagine how this thing might look like, just as a rough sketch. The origin is going to be one of the points, so that's going to be a point on the plane. One point is P, that has a 4, -1, 5, so I'll put it over here, P, and then the Q is 5, 1, 2. It's a little bit lower over here. Let's call that Q. And then our X, Y, Z space. And then this is our origin. That's one of the points on the plane. So we can imagine that the plane, I don't know, maybe kind of looks like this somehow, and that contains these 3 points. So that's the important part. Now we have 3 points that are on the plane, and we want a vector that's going to be perpendicular to that. So we have 3 points to choose from. That's not going to be an issue. But the normal vector, how are we going to find a normal vector? What we can do is that we know we can extract, or we can construct a normal vector if we have 2 other vectors that are on the plane. Well, we have 3 points. We can certainly create 2 vectors, and the easiest vectors to create are the vectors from the origin to the point P and the origin to the point Q. In fact, those 2 vectors, because they're in standard position, we can just change these parentheses into the angle brackets that we use for vectors, and call this one vector P and call this one vector Q. So we have these 2 vectors that will give us, that when we take the cross product, these 2 vectors can give us a normal vector. So whatever we do when we cross them, we're going to get a vector that's going to be perpendicular to those 2 vectors. And since those 2 vectors are on the plane, then this vector will necessarily have to be perpendicular to the plane. All right, let's find that vector. So our vector n is going to be the cross product of P and Q. And the cross product setup is I, J, K. We have the P vector, that's a 4, -1, 5, and the Q vector 5, 1, 2. All right, let's see, the I component. The I component will be a -2 minus 5. I believe that's a -7. I'll throw a negative sign for the J. It's going to be a +8. This is going to be a +8 minus, get lost here, 8 minus 25. So 8 minus 25, 8 minus 25 is -17. So that negative sign and a negative sign will make this positive. So we'll fix that. Oh, let's do it now. And then the last component will be 4 minus -5. So that's 4 plus 5 is 9. Okay, so we have our normal vector. Now that we have our normal vector, our equation will be -7x, and this is a +17y, and then +9z is equal to something, is equal to d. We have not computed that yet, so let's do that now. D, remember, is equal to the normal dotted with any of the points that we have here. Guess what? One of the points is the origin, so if we dot that with the origin, then this is just going to be 0. So origin is a vector 0, 0, 0, and the dot product will result in a 0 scalar. So that should be our answer. Now, just to prove to you that it doesn't matter which of these points we dot, we should still get 0. I'm going to dot it with, let's dot it with 512. So let's find N dotted with Q. Now, we don't have to do this anymore because we already have the answer, but I just want to show you that it doesn't matter which one we choose. So we have a -7, 17, 9, dotted with 5, 1, 2. So we have -35, we have plus 17, and then 9 times 2 is 18. So I believe this is going to be 5, well, that's going to be 35, minus 35 is going to be 0. So that is going to be a result. Just to finish this off, let's take a look at a Desmos or CalcPlot 3D look. We have these 3 points. I didn't highlight the origin, but the origin is going to be the 3rd point. So we have these 2 points, and then we created these 2 vectors that are connecting those 2 points and the origin. And then we crossed it, so the cross product gave us a normal vector. So I already have the normal vector figured out over here, and it looks something like this. And it does, it's at the correct angle, it looks like it's actually going to be the right angle. All right, once we have that, we can draw the equation of the plane. Let's use an implicit surface again. And this is a -7x plus 17y plus 9z equals 0. And when we see that, okay, oops, this is supposed to be 9. Thank you. All right, now it looks better. So those 2 points, as well as those 2 vectors, are actually on that plane, and that normal vector is in fact perpendicular to that plane. So I think we're all good here. Okay, so I hope that helps us find equations of planes. There's going to be some problems where you have different things that are given to you, but the bottom line is you need 2 things. You need a point and a normal. Once you have that, you're all set. You can find the equation of plane. All right, good luck, have fun.